Okay, some of the things I say today are just review of yesterday, all right? But we're still studying the complex plane and Demoivre's theorem. By the way, Demoivre's theorem is probably one of the most beautiful theorems you'll see in all of high school math. Maybe as beautiful or even more beautiful than some of the theorems we learn in calculus. And those are pretty amazing facts. So I don't want to go too fast through it. I want you to have your calculator ready so you can play around with these ideas yourself and learn them through investigation too. Okay, so what did we learn to do yesterday? Yesterday we learned how to take, we learned how to plot. Let's write down all the things we know. We know how to plot a complex number. And we'll review that again today too. So check. We learned how then to convert a complex number in rectangular form to polar form. Check. It's actually just two formulas. We then learned how to convert back again. So convert from polar back to rectangular. Check. And then I ended with plotting. Plot a polar form complex number. So if you were here yesterday and you took notes, or if you watched the video, then you have these 4 skills. Okay? All right. This is just the start of an interesting topic, though. So let's go now and just write down our formulas. So what we did was to convert from rectangular form to polar form, we used the fact that the absolute value of a complex number is its distance to the origin, which really just looks like r equals square root of x squared plus y squared, but we're using a's and b's instead of x's and y's, and absolute value z instead of r. We also said that this has a name. It's the modulus of z. Modulus. I did not invent the word, okay? Then we also talked about theta. Theta is what else? The other thing you need if you wish to write in polar form, and that is formula inverse tan y over x. And you're supposed to add 180 if and only if, IFF, if and only if a is negative, and I'm not supposed to be using y and x. It's supposed to be b and a. Sorry about that. B over a. I'll try to be consistent, okay? You're supposed to use b and a for this. But if a is negative, and only if a is negative, you add 180. And this is just because the calculator does not understand quadrants 2 and 3 at all when it comes to arctans. And it shouldn't. Okay, converting from polar back to rectangular form doesn't even require equations. You just basically distribute. And plotting a polar form of complex number is just identifying what it means and plotting. So you don't need formulas for that. Let's just go on and try something here. First thing I'm going to have you do is I'm going to give you 2 complex numbers, z1, 2 plus 3i, and z2, negative 3 plus 5i. Let's make it a little more interesting. Let's do negative 7 plus 5i. First thing I want you to do is plot them. Okay? On the same grid. Ready to go. Label them Z1 and Z2. Okay, so 2 plus 3i you should have plotted here. You can just label it Z1. Negative 7 plus 5i is over here. This is Z2. And now I'd like you to draw their moduli. Draw their moduli. That means their r's. Draw their r's. Each one has its own r, or distance to the origin, or absolute value, you could say. There's R1. And there's R2. Okay, good. Now I'd like you to find their sum. So I'd like you to add these numbers together. So I didn't even teach you how to do that. Your Algebra 2 teacher did. So add these two together. Find the sum z1 plus z2 Okay, so how do you suppose we should add complex numbers? What do you guys think the sum is? It's pretty straightforward, actually. Probably -5 what? Plus 8i. Yeah, you're just going to add the reals together, add the imaginaries together. Right? The I is very much like x. It's like a variable. So you're supposed to add the reals together, -5, add the imaginaries together, that's 8. Now plot it. Plot it. You've got your graph paper there, plot it. And label it. Okay, there's two things I'd like to mention here. First of all, anytime you add, subtract, multiply, or divide complex numbers, you end up with a complex number. That in mathematics is called closure. Closure means no matter what you do to a complex number, or what you do with two complex numbers, you always end up with a complex number. In other words, you end up with another point somewhere on this plane, namely the green one. Yes?
What is in I times I -1?
Yeah, and that's on here too. -1's right here. It means -1 plus 0i. It doesn't matter what you start with. If you have a z1 and a z2 and you multiply them or add them or divide them or even put them in powers with one another, you always end up in a new spot on the plane. Okay? The second thing I want you to notice is there is a parallelogram here. Okay? It might not be visible to you right away. But if you connect z1 plus z2 to both of the original addends, you can see there's a parallelogram chilling right there on your paper. And the modulus of z1, z2 is its diagonal. This is a very important concept in physics and in vectors. So we will see this show up again in section 8.4. So what did I do? I had you plot 2 points and draw their moduli. I had you plot the sum and draw the modulus. And you can see there's a geometric interpretation here. The sum, the modulus of the sum of two complex numbers is the diagonal of the parallelogram formed by the addends using them as adjacent sides. Now you kind of have to imagine those two blue dotted segments, don't you? But it's always there, and that always works. You can always form a parallelogram. Okay, so a little side fact there. This is a parallelogram in complex, on the complex plane. Okay, now you can also subtract complex numbers. Suppose you want to find z1 minus z2. That's not hard to do. If you want to subtract, how do you suppose you would subtract? What's 2 minus -7? 9. What's 3i minus 5i? -2i. And you could plot that too if you wanted. Let me write that in purple. I'm kind of color coding everything today. I'm saying that you could do a subtraction and you get 9 minus 2i. And that too has an interesting geometrical interpretation. This point over here But I'll let you think about it later. How do you think the two red segments tie in with the purple one? I'm not going to go over it. We'll talk about it later when we hit vectors. Okay, it too is the diagonal of a parallelogram. It's just, the parallelogram is a little harder to see here. Okay, let's go on to multiplication. So I have 2 plus 3i and negative 7 plus 5i. Can someone just double check that I copied those correctly from the previous slide? Okay, I'd like to multiply them. Okay, so if I'm going to multiply these, I don't think I can do it in my head as easily as I did when I added, you know? So I'm just going to go ahead and write down what it means. I'm going to multiply these together. Okay? And it looks like I'm going to have to do a FOIL, right? First, outer, inner, last. Okay, so 2 times negative 7, 2 times 5i. Inners is 3i times negative 7. Lasts are 3i and 5i. Okay, everybody say hello to the I squared. Everybody say hello to that I squared. Now say goodbye to the I squared. Whenever you see an I squared, say hello. Change it to a negative 1 and say goodbye. Because I squared is negative 1, right? Okay? So what happens is the first and the last terms in the FOIL are always real numbers when they're written in a plus bi, c plus di form. So basically you're going to put that first and last terms together. There's a negative 29, isn't there? And the two I terms go together, minus 11i. Sure enough, there's closure. There's another complex number, a plus bi. Now, we're going to graph them. So we're going to graph z1, z2, and the product z1, z2. And there's a very interesting geometric interpretation here. So let's go ahead and draw them. So you need lots of space for this one. Z1 was, I can't remember. What was it? Just 2 plus 3i. Okay. So right 2 up 3. I'll do the red again. And go and draw the modulus. Z2 was negative 7 plus 5i. Left 2, 3, 4, 5, 6, 7. Up 2, 3, 4, 5. So that's this point. And the product took a while to get. But the product was negative 29, negative 11i. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, down to 3, 4, 5, 6, 7, 8, 9, 10, 11. There's my product and its modulus. Now this was a little harder to see at first. You might not see it. It's not a parallelogram anymore. But there is a very fascinating geometrical interpretation of all this. The picture means something. That's what I'm saying. The picture means something. See some triangles? No, there's no 3D here. In fact, it's not even two-dimensional. All of this is a number line. Okay? These are 3 complex numbers on a number line. We had them represented in 2 dimensions because of the imaginary part. Okay, you might not see it, but you will in a minute. You see it? What is it?
Is it the, what is it, theta equals r?
Theta equals r.
I can't remember.
Are you saying you see a symmetry here?
No, I see the
see a spiraling out effect. Yes, multiplying two complex numbers will create a spiral effect. We'll see that in a minute. Okay, the actual geometric interpretation of this is a little hard to see, and it's because we are in rectangular coordinates right now. So what I'm going to have you do right now is convert Z1 and Z2 and Z1, Z2 into polar form. And then it will pop out at you in no time. So get your calculator ready. We're going to convert all three of these numbers into polar form, and if you miss it, I'd be shocked. But if you see it, you're going to be shocked. Okay? It's pretty cool. All right, let's do this. So Z1 was 2 plus 3i. Let's have Jace's row convert that one to polar form, and maybe also Cole's row. So I want that thing in polar form. And then let's have Matt's row and Jessica's row convert Z2 to polar form. That's the negative 7 plus 5i. And then let's have the last row, that's over there, Caitlin's row. Let's do the Z1, Z2, the product, okay? Keep your calculator in degrees mode, even though you used radians maybe last night, okay? You will not miss this. It'll definitely stand out at you. Converting to polar means use Pythagorean theorem to get the modulus, use inverse tan to get the argument, and write a modulus cis argument. Modulus CIS argument. And this will be our concluding interesting fact of the day. Tomorrow we'll talk about what Demois did with all this and how he wrote his amazing theorem. Although we won't be ready to prove it yet because we don't know induction yet. So, okay, so if you perform the modulus calculation with a 2 and a 3, you're going to get rad 13 because it's 4 and 9 and then square root. So hopefully for Z1, somebody in the room got root 13. And then it's CIS. And what's my angle? You're supposed to do arctan 3/2. I don't have my calculator handy, so let me find it here. Here it is. Arctan 3/2. And decimals degrees is fine. So we have 56.310. Okay, so hang on to that guy. Z2, you're using a 49 and a 25, right? So 49, 25, 74. Root 74. CIS, now you got to be careful here. You're doing 5 over negative 7, so inverse tan, 5 over negative 7. But don't forget to add the what? The 180, because what's negative? The first real part, yes. So 144.462. And Caitlin's row, kind of a weird answer, but what do we get for our modulus? Square root of 962 CIS and inverse tan. Now, do I add 180 on this one? Inverse tan, negative 11 over negative 29. Do I add 180?
No, negative 11.
What's the rule? When do you add the 180?
When it's in quadrant 2 or 3.
When A is negative, add the 180. A is negative. Doesn't matter what B over A is. The rule was A is negative. The angle here is, give me 15 more seconds, 200.772. Well, that was kind of cool, but that was weird. 200. Huh, look at your three arguments. 56, 144, 200. Interesting. 56, 144, 200. Anyone see a connection there? It seems like the argument is the sum of the arguments. We were doing a multiplication problem, remember? Interesting. Look at the moduli. Root 13, root 74, root 962. Isn't this just the product of these two? So the modulus is the product. The argument is the sum. Very cool. Tomorrow we'll talk more about that and where it took Dame off. Okay?